Hello everybody, I'm back with another video. This time I wanted to talk a bit about standard errors and confidence limits. I know that this is a topic that is little difficult for most people to understand because it is never explained properly, and also I think it has ramifications in almost every other basic concept which underlies the entirety of statistics. So I think I'll try to cover it in whatever the most easiest to understand way possible. But let's see what comes out of this. Okay. So today will be more of a theoretical lesson, less of practical using Jamovi. I hope that this class is useful for you. So let's just get on with it. I'll share my screen now. Okay. So yeah. So, as the title says, I'll be talking about errors and biases. In that, the main error that we'll be talking about is the standard error and what all it means, and from that, consequently, the confidence limits. And over the course of this video, you will understand how tenuous it is and how removed it is from reality and why it seems like a scam most of the time. And maybe I'll try to give you an idea which can help you with better estimation of confidence limits. Although it's a little difficult to use, but let's see. Okay. So the first is let's start from the very basic. Okay. Like what is the point of a research study? Research study is mainly meant to find out something which is not very well known. Okay, like that's the core of research, like something that is not well known, you want to improve upon the knowledge base, right? Now, if you wanted to discover something completely, meaning that if you actually wanted to find out anything about a certain topic or variable completely, you will have to have complete knowledge of it, meaning that you will have to have all of the data points which have ever existed and are existing currently, right? Now, the problem is that that type of thing is almost impossible to achieve in practice. Like countries maybe can go ahead with doing a census. That too is a huge exercise, and mostly it is a very expensive exercise also. And even in that, it is not completely correct, meaning that it is never completely accurate. By the time the census gets done, the data would have changed, right? So you would never have any practical way of knowing the entirety of the data, and hence you will never be able to come to a completely 100% certain conclusion of whatever knowledge you are trying to acquire. Okay. So it is basically impossible. So what we can try to do to get around that, as is the common thing in scientific community, what we try to do is we try to take a sample from the population and we try to extrapolate whatever findings we have to the population. So basically we get partial knowledge, that is basically getting it from the sample, that is partial knowledge, and we try to extrapolate it to the entire population with certain checks and balances. Now, the thing is that whenever you are drawing any conclusions from a smaller subset of the entirety of the population, you never know how good or how reliable whatever you're trying to find out is within your data, right? And also, you have no way of knowing how far removed from the truth it actually is, because you have no idea about what the truth will actually be, because you do not have the knowledge of the entire population anyway, right? So it's like a very weird answer to have, because like you're trying to extrapolate from the if you know the Matryoshka dolls of Russia, you know that it's like doll within a doll within a doll within a doll type of thing. So imagine you're taking the innermost tiniest doll and you're trying to use it to extrapolate to the largest doll of that entire series. So that will definitely come with some sort of problems in extrapolation, right? And because you do not know what the actual biggest doll looks like, you will never really be able to reduce it. You'll never be able to know how wrong you are also, right? So all we can do is mostly assume certain specific factors, and based on those assumptions, we try to ascertain how far removed from truth we actually are. Okay. So now let's talk about two specific words, errors and biases. In statistics, you will be hearing these words being spoken relatively frequently. Now, the point of this is like when we think about it, it seems like a bias should also be an error, right? Now, to reduce this confusion, we'll include two specific terms. That is, all biases are errors, but not all errors are biases. Okay. Now, in research methodology, your biases are specifically the term used for those errors in measurement for whom the cause is known. Meaning that suppose you are trying to measure some specific variable about some specific thing that you are studying. Okay. To use that, you are using a certain instrument. Now, suppose that instrument's calibration is wrong. Okay. So that is basically if you correct the calibration of that instrument, the errors in your measurement will go away. Right. So that type of error is called a systematic error or a bias, meaning that the cause of the error or the deviation from the truth is known, and you can correct it by improving your instrumentation or methodology of research or whatever steps you want to take to improve it. Basically, it is known and can be improved upon. Coming to the other side, there are certain errors in measurement that you will never be able to take care of, because by default you do not know the reasoning for those errors, the cause of those errors. Okay, so those errors are known as random errors, and these random errors crop in whenever you are taking a subsample of a big population. Okay, so there will be many such reasons for them that we do not know. And as soon as we come to know the reason for error in the measurement, that basically becomes a systematic error or a bias. Okay, now all of these other errors are clubbed into a term called random error. Okay, now this random error is technically uncorrectable, meaning that since you do not know the cause, you cannot really remove this error. However, you can hope to lessen it, like reduce that error by going as close to the population as is feasible. Meaning that if you have this big of a population and you're taking this tiny of a sample, then obviously there is going to be error in measurement, right? And that is going to be the source of random error. But if you had this big population and you took this big sample size, then you are reducing that random error by a wide margin, because you are basically taking everything, most of the population into your study. Now, most of our studies are funded, means basically they require monetary resources, also our human resources as well as time, right? Now these are the primary factors which constrain any study design. Now, because we do not have infinite of any of these, we will have to curtail our study to a certain degree, and mostly it is curtailment to a large degree, meaning that we are usually able to take, like I said, this big population, and we are actually able to take only this big of a sample from that population. So there's not much you can practically do about it, right? Now, let's go on to the next one, that is now standard errors. Now, when we talked about random error and the way we cannot improve upon them, quantifying of that random error, though, is important for us to know how certain we are of whatever we are measuring. Okay, so let's, for this, for the entirety of this lecture, let's call this, whatever you're trying to measure, as an estimate. Okay, so you're trying to estimate some variable. Okay. Now, this estimate, you will have errors in measurement, meaning that whatever is the truth of that estimate in the population, your sample estimate will be a little farther removed from that. Okay. Now, how do you know the error in the measurement when you do not know the true estimate anyway? Okay, so for that, the assumptions that are used are broadly two. One is that if your data, the sample data that you have acquired from the population, if that sample data is widely dispersed, meaning there are too many outliers, or it is just widely dispersed in itself, then you know that your estimate might be wrongly produced. Okay. Second point, if your sample size was too small, okay, meaning that basically what we established was that as you go towards the sample size of the population, like the entire population size, as you go towards that, the error is supposed to reduce, right? So basically, whatever random error you are going to have and its estimation, that is standard error, is going to be inversely proportional to the sample size that you are getting. Okay. Now, these are the two main assumptions that we are using when we are trying to compute an estimate of the random error within our sample, and that is called standard error. Okay. So I want to present this with an example because this way I think that it will make more sense. So what I did was I went to the 2021 census, and from that census data, I picked up the height, the mean height of all of the states as was measured at that point of time, and I focused on the mean height of Karnataka. Okay. I assumed that the dispersion in the height would be around 3 centimeters, meaning I took the standard deviation. I assumed that again to be 3 centimeters, and the mean height of Karnataka I took. And using these two variables, that is the mean and the assumed standard deviation, I was able to randomly generate the height distribution of Karnataka residents. Okay, so the sample size I took was the population of Karnataka at that point of time, that was 52.8 million. And using that, I generated the random data, and this is the histogram of that randomly generated height data of Karnataka. Okay, so this looks perfectly symmetrical, mainly because we have had a huge sample size to play around with. Like basically, I generated a huge sample size. This is basically what we are taking as the population. Okay, so we have generated a huge population data, and because I'm using a normal distribution for generating the this random data, it will look like this. Okay, now what after that, what I decided to do was to sample this population that I generated at various sample sizes, meaning that I started from a minimum of 5 sample size and went up to a sample size of 1,000. Okay. So I generated such 1,000 samples from this population, and I drew out their histograms, and I have collated them in this video that I'm going to play right now. In this, you will notice how the distribution, the shape of the histogram changes as you go from a small sample size to a relatively large sample size. Okay. So yeah, you can see that the sample size is changing at the top. Okay. And the histogram is being displayed. Okay. When we started, let's start again. Okay, wait. Let's start it again. Oh, sorry. Oh, I hate PowerPoint. So you can see that when the sample size is small, that is at 15 sample size, you can see that there is a spread of the height. Okay, you can see that there are this many heights which have been collected, and most of them are a single in number, and there is one height, I think, which is 169 or something, 169.5 or something, which has got two samples. Okay. Now, as we go up the sample size, this distribution will slowly change and start to resemble a normal distribution. And along with that, you will also notice that the number of samples will obviously increase, and the frequency along this axis will also keep increasing. That is but natural, right? So it will scroll through them very quickly. Now you can see that slowly the semblance of a normal distribution is starting out. Okay, in which you will basically have a single peak, and you will have very less height as less number, and very larger height as also a smaller number. We have reached 500, and here also you can see that it has reached the normal distribution type of shape, and the same shape will be retained until it goes up to 1,000. I'll just let it play out. You can just see this. Now, this is to show that you can achieve a semblance of a normal distribution histogram quite early, meaning that you don't need thousands of samples. You will usually get that type of distribution at around 100 sample size. So technically it is said that it will be around 30 to 50, but I usually say that bigger the better. So let's just go and see. So see, you're still at 70. Okay, it still doesn't look. Okay, look like at the 100, it starts to look like a normal distribution. And after this approximate shape stays retained. Okay, so that is why I suggest that always go for a little larger sample size, like up to 100 at least. But again, the actual distribution, the actual number of samples that you want will depend on the distribution of your original data, and that you will anyway never know. So you will have to make assumptions about that by judging from your clinical acumen or domain expertise, basically. Okay. Now so basically in that I had shown that I have collected sample sizes from small number, that is 5, to a large number, that was 1,000 sample size. Okay. Now in the next stage, I want to show you how your confidence intervals, what exactly confidence intervals mean. Okay. And what exactly standard error means. Okay. So for that, I'm doing another exercise here in which I have taken that population, and from that I have sampled 1 lakh samples, each with 20 sample size. Meaning that earlier we were increasing the sample size as we were sampling. Now I have sampled only 20 sample size, and in that 20 sample size, I have collected almost 1 lakh randomly sampled data sets. Okay. Then I have drawn density plots of those same 20 sample, n equal to 20 sample data sets. And you can see how variable they are in their density plots. You can see that there are so many of them, like some of them have the middle point quite less. Some of them have middle point quite large. The actual mean of this population was 166. Okay, so 166 will come somewhere around this region. Sorry, 165, 166 will come somewhere around this region where most of them are peaking out. But quite a few of the samples you will see have much lesser peaks. Some have quite larger peaks. Some are quite narrowly distributed. Some are quite widely distributed. There are some which are like so widely distributed that they don't even have a well-known, well-seen peak also. Okay, so this is just to show you that when you are randomly sampling from a population, you can literally get any type of distribution. You understand? Like you have no guarantees that you will be able to replicate the population as closely as the population itself is distributed without going for much larger sample sizes. Okay, that is the only guarantee you have of getting the population distribution accurately reflected in your sample. The larger you go, the better it is. If you go for small, you never know what you are getting. Okay, so quality of data basically becomes suspect at smaller sample sizes. Okay, now that I have generated this 1 lakh samples of n equal to 20, what I did was I calculated the mean height of each of those samples, and I have plotted that as a histogram in this figure. Okay, so you can see that the mean height of each of those samples, so the mean height of the population was 166, and you can see that that is where the maximum number of that is where the mean of maximum number of samples is. Okay, so each of these bars has a bin width, that is, it is of 0.2. That means that it is ranging from 165.9 to 166.1. Okay, so within this bin width has the largest number of sample means. Okay, but there are a lot of sample means which are smaller also, a lot of sample means which are larger also. And the interesting thing to see is that because the population itself was normally distributed, the distribution of the means of those randomly sampled data sets is also looking like a bell curve. Okay, this one interesting thing. You understand? Like if you sample from randomly from a population, you will eventually, the summary statistic of each of those samples is going to resemble, the distribution of that is going to resemble the distribution of the parent population. Okay, chalo. Next. Now that we know that the estimation that the actual mean of the population was 166. Okay. And now we have a distribution of sample means. Okay. So we have got a wide ranging sample means from almost 163 point something to 168 point something. Okay. Now each of these which have any number, any mean which is different from 166 is basically an error in measurement, right? That's what error means, difference from the true estimate. So I have quantified that difference of true estimate as a measure of dispersion basically, and that dispersion or the error has been plotted as a histogram in this plot. Okay, so the true difference should be like if you were completely accurate, the difference should be exactly equal to 0. Okay, that is what the green line here is, and you are seeing that the errors are also distributed around that 0, ranging from somewhere around minus 2 point something to plus 2.9 maybe. Okay, centimeters. Okay, and so now we come to the definition of standard error. Okay, the standard deviation of these errors in measurement when you have sampled the original population infinite times is called the standard error. This is what it conceptually means. You understand? Like conceptually, if you sample the parent population infinite number of times, okay, using the same sample size as your study, okay, then you will get a distribution of the errors in the mean, and the standard deviation of those errors is defined as the standard error of mean. Okay. Now, this concept basically is applicable to other types of standard errors also, meaning that and this is just the standard error of mean, like you're trying to estimate the mean. Sometimes there'll be mean difference, that also technically is a mean. Suppose correlation coefficient. Okay, correlation coefficient also will come out as an estimate. Okay, what the confidence intervals of that correlation coefficient will mean is that if you did your study the same way infinite number of times from the parent population, then the range of the like basically your the error in your measurement or estimation of the correlation coefficient is going to lie between that end and this end of the using by the standard error. Okay. So basically, if we go by the meaning of standard deviation, like because we established that the standard deviation is like your standard error is the standard deviation of the errors in measurement of the mean. Okay. Now, what does the standard deviation help us with? It means that if we take plus minus 2 standard deviation around the mean, as per the normal distribution characteristics, if we take plus minus 2 standard deviation about the mean, 95% of the entirety of the errors in measurement should come within those. Okay, only 5%, that is 2.5% on one side and 2.5% on the other side are left out. Okay, but 95% of the errors should come within those two limits of plus minus 2 SD. Okay, so here basically it is plus minus 2SE about the mean. Between these two limits, 95% of the times your estimate should lie. Okay. Now, yeah, so that is what. So in if you are talking about correlation coefficient, then the whatever plus minus 2 times the standard error about the correlation coefficient, if you calculate 95% of the times your correlation coefficient, if you did the infinite sampling and did correlation coefficient of each of those, will lie between these two limits. Okay. So now what I have done here is that because now we have sampled it infinite number of times, like here it is not infinite, it is 1 lakh times. For each of those 1 lakh samples, I have calculated the standard error using the formula which is used in the analytical approach of calculating standard error. Because most of the times we will not be able to determine the standard error by ourselves because we do not have any knowledge of the parent population, right? So there's a random sampling and all things we cannot do. Okay, so we have sampled one. From that, we have to make out how the standard error is. Okay, so that standard error gets calculated using a standard formula. Okay, for standard error of mean, the formula is the standard deviation of your sample divided by square root of the sample size. Okay, that gives you the standard error of mean of your sample in your study. If it is a standard error of mean. Okay, like that, there are formulae for other standard errors of other estimates. Standard error of mean is this. Okay, so I calculated the standard error of mean for all of the samples that we right now collected, that those 1 lakh samples. And in that, you can see that it is that standard error is also ranging from a very low number to a very high number, while the actual standard the actual standard deviation of the errors in measurement was 0.671. So this is like the theoretical standard error that we have, and the calculated standard errors are widely distributed around this actual standard error that we have determined. Okay, based on the concept of it. Okay, so this basically tells you how widely variable your calculated standard error, even like your estimation of the error also has an error inside it. You get it? So because of that, I say that you will never ever be able to be certain about anything using statistics, especially when it comes to biology, because there'll be a huge amount of variability anyway. There's an inherent amount of variability anyway inside that. Okay. Along with that, but I also did one interesting thing, that I averaged all of these standard errors that came out, and the average came out to 0.664, which was respectably close to 0.671, but that is also going to be there because it's the unimodal distribution, which is symmetric and so on and so forth. So the middle point will lie at the middle point. So basically they are almost the same, but that doesn't help your case. This is just an interesting side finding. Okay. The main takeaway from entirety of this right now, whatever we have discussed, is first that the concept of standard error is that it is the error in measurement of your estimates from the true estimate if you have sampled infinite number of times. Okay, so infinite samples, you calculate your estimate in all of that. You have some idea about the true estimate, you minus all of those, and whatever is the standard deviation of that, that is just standard error. Okay, now that is the concept of it. Practically, how we do it, because practically we have no knowledge of the basic of like basically what the parent population will look like and whatever the estimate in the parent population will look like. What we do is we have come up with some analytical methods of calculating the standard error, which are going to estimate the standard error for us, and we just have to blindly trust that that is a good enough estimate. Okay, so it is basically good enough estimate of the goodness of your sample. Okay, sample estimate. So that is how it is calculated. So basically, one is conceptual, one is practically how it is done. Okay. Next, we'll talk about confidence limits and how that is basically the practical application of the standard error. The confidence limits, will come to that soon. Okay. But before we do that, I wish to take a small break. I'll drink some water and then we shall continue. Okay. All right. Let's come back to it. Now we shall be talking about errors. Now, until now, we were talking about errors in measurement. Now we'll talk about a certain types of errors, which are called alpha and beta errors, as well as power and p-value, which are some other confusing topics for most of the people who start studying statistics. Okay. So in this, I try to teach it in a way that imagine that you are living in two sets of realities. Okay, one is the true reality. True reality means that the reality which is of the population itself. Okay, basically you have some idea about the population, and in the population, whatever is the reality is the reality. Okay. Next, you have taken a sample that is basically your reality. Okay. So you are dealing with two sets of realities here. Okay. Both of these realities can be yes or no. Okay, like basically whatever question you are trying to answer, if you binarize the answer to any question, it can become yes or no. So in your actual reality also, you can have yes or no, and in your study reality also, it can be yes or no. Okay. Now, if your real reality, that is in the population, the answer to your question is no, but your study reality, it concludes yes. Okay, then you are committing an alpha error. Okay, now this is important because most of the time when we start a study analysis or hypothesis answering, what we usually assume is that the reality is a no. That is a null basically. Okay, so reality is no. And if we refute that null, that is we answer yes, then that is our answer. Okay, then we are able to correctly trust our result. Okay, now if your actual reality is no, that you will never know. But if your actual reality is no, and your study reality is yes, okay, then you are committing an error, which is called alpha error. Okay. Next, if your actual reality was yes, meaning that in the population, the answer to your question was yes. Okay. And your study reality concludes no, then that is called a beta error. Okay. If the actual reality was yes and your study reality was also yes, then that is basically the opposite of beta error. And that is what we call power. Okay, so the estimate of true reality being reflected in your study is power. Okay. That is like pretty easy to understand also. Like basically you're powerful if you get the correct answer, right? It's like that. Okay. Then the next thing is p-value. P-value is the estimation of alpha error. Just think of it like this. Like p-value is alpha error. Alpha error is the concept, and the estimate, that is the probability within that alpha error, is your p-value. Okay. Now the thing is that whenever we conduct a study, we have to set alpha error tolerance limits, meaning that we cannot ever completely remove alpha error because we will never know the true population anyway. Okay, we will never know the real reality anyway. Okay, so we have to set some tolerance level for alpha error. Okay, and that tolerance level, basically, if you are okay with 5% tolerance of alpha error, like 5% of the times, if your study concludes yes and the real reality is no, you are fine with that. Okay, as long as it is less than 5%. If it is more than 5%, then you cannot trust your results. Okay. So that is what your p-value basically means, that 5 less than, if your answer is statistically like the p-value less than 0.05, basically means that there is a less than 5% chance that you are finding out an answer which does not exist in reality. There is a less than 5% chance of that. So there is a more than 5% chance that you are certain of the quality of the estimate you are getting. Okay, so that is what p-value basically means. Okay, now usually it is set at 5%, but if you are like, if you want to be really, really sure, okay, you can take it at 1% also. That is up to you. The lower, the better, basically. But that will require larger sample sizes. Okay, or the association or whatever you're trying to measure has to be a really strong estimate. Okay. The other flip side is that if you want to increase your tolerance limits, meaning that you want to be okay with 10%, you have to be really, you have to give a proper justification for that, because most people will not accept of 10% alpha error limit. Okay, so justification can be like whatever you are trying to study has a very low rate of occurrence in the population, maybe, or whatever you are trying to study is not possible because of the resource intensiveness of whatever you are trying to do, like your resources are less than what is required, so on and so forth. So basically, it comes down to resources and feasibility. If you deem it infeasible and you are able to justify that infeasibility to your reviewers or readers, then basically you can take at 10% and be okay with it. But the universal opinion is that of 5%. You can go down to 1% and be very happy with it. There is no problem about that. Okay. Now let's talk about confidence limits. Okay. Now, like I said, that SE, standard error, is theoretically the standard deviation of your errors in estimation away from the true mean. Okay. So basically, your sample mean is in between somewhere. Okay. And around that, it can vary to this much extent. Okay. If you repeated your study infinite number of times. Okay, so basically it is the hypothetical outer limit of expected measure if you had sampled infinitely within your given population. Okay, now as I had said before, like these limits to which you want to adhere yourself are given by the alpha error, meaning that if you're talking about a 95% confidence limit, or that also means 5% alpha error, like 100 minus the alpha error becomes the confidence limits. So that basically means that if your estimate is in between and you have got confidence limits on both sides of the estimate, 2.5% this side, 2.5% that side. Okay, those are the outer limits of your estimate. Okay, now this technically is a precision measure, because in this has not as much to do with your sample as it has to do with extrapolation of your sample data to the population. Okay, again, let's recap. You have gotten some some estimate from your sample. You want to extrapolate it to the population. So for extrapolating to the population, you have to be certain of your result. For being certain of the of your result, you need to be able to calculate the error in estimation. Now that error in estimation is calculated by the standard error. You set your limits that 2 times standard error here or there, I am okay with. That covers 95% of your variability in your estimate anyway. Okay, so 2%, so your estimate plus 2 standard error, and your estimate minus 2 standard error, that is going to be your confidence limits around your estimate. Okay, so that is basically because now what you're saying by presenting those confidence limits is that if you did your study in the same way from the same population infinite number of times, your estimate is going to lie between that level and this level. One end of the confidence limit to the other end of the confidence limit. Got the idea? So that is the practical utility of standard error. So there are three ways in which we discuss the standard error. One was conceptual, that is the infinite sampling and the error in estimation. Second was the mathematically how it is calculated. Okay, that is the closed form formulae that have been described for various types of estimates that you're trying to do. And third is the practical utility of it using your confidence limits. Okay, so these you need to understand your standard error in these three formats. Okay. Next, how do your confidence limits, that basically means standard error, how does your standard error or confidence limit change with increasing sample sizes? Okay, you remember that we had done increasing sample sizes in the beginning, like basically how the distribution changed with increasing sample sizes. For those same, I increase the number of samples to 2000. Okay, so basically from 5 to 2000, I have steadily increased the number of samples within each of those random samplings that I did. I calculated the mean of all of those. Those means have been depicted as the dots in this graph. And I also calculated confidence limits for each of those estimates. And those are plotted as the bars above and below. So they are the upper confidence limit and lower confidence limit. Okay. So now that I have drawn that, you can see how as your sample size is increasing along the x-axis, you can see how the width of your confidence limit keeps on reducing, because that's how the standard error is calculated, right? Standard error is inversely proportional to the square root of your sample size. And because of that, it is going to go down very rapidly as your sample size increases. Okay. So you can see how it is following a downward sloping path of the upper confidence limit and an upward sloping path of the lower confidence limit as you increase the sample size. And that reduction is going to continue, albeit in a very gradual manner as you keep increasing your sample sizes. Okay. So this is how your confidence limits change or standard error changes once you increase your sample size. And a maximum amount of that change would have happened within the first 100 samples or so. And after that, the reduction is pretty gradual. Here, that maximum change is happening up till maybe 250 odd. Okay. And after that, there's a very gradual change in the reduction in the confidence limits. Okay. Now, the bottom line of this entire exercise was that you basically have to get used to the fact that nothing you ever research is ever going to be 100% certain. You are never going to be certain because you do not know what the total population itself is. Even if you knew what the total population itself was at that point of time, in subsequent periods of time, that population is likely to change. And your results may not be 100% applicable to future populations also. So just be okay with knowing that whatever you're estimating is going to have a lot of errors in itself, and you just have to try and show that you did your study well, and whatever your uncertainty was, that you have tried to reduce it as much as possible by taking care of systematic errors or biases, by improving your research design, and also by increasing your sample size and sampling effectively to reduce your to reduce the dispersion within your data set, to reduce your standard error. Okay. So these are the only two things that you will be able to do. And as like philosophically in life also, this is a very useful skill to have. Nothing is ever certain. Okay. Nothing is ever going to be certain, whether it's in the present or in the future. Things are always going to change. You just have to be okay with the uncertainty and do things as best as you can given the resources that you have. Okay. Like I'll be doing a lot of such philosophical talks while I'm explaining statistics, because I have in my life and sort of career as a statistician, I have seen that a lot of the principles in statistics can be applied to real life also. Okay. So here, there is one more aspect of the confidence limits that I wanted to point out. This is an important thing. So, like I said, your confidence limits will lie between plus and 2 plus minus 2 standard error of your whatever estimate you have had. Okay. Now, if those estimates, okay, they are like, okay, let's start with an example. Suppose you wanted to see the difference, mean difference between two groups. Okay, difference of means between two groups. Okay, so you have two groups. You subtracted, you basically calculated the means. You subtracted the mean. You got a pooled standard deviation, and for that difference of the means, you calculated standard error and you calculated confidence limits. Okay, now if your one of the groups is larger than the other, suppose. Okay, so whatever your estimate you are taking in one of the groups, that mean is larger than the other. Okay, so that mean is going to be positive, suppose. Okay, that mean difference is going to be positive. Now, if within your calculation of confidence limits that went from a very low number on one side of your mean difference to a very large number on the other side of your mean difference, if your this limits, if they straddled the 0 point, meaning that 0 is the point of no return, meaning that if the mean difference was exactly 0, there would be no difference between the groups. If the difference is positive, meaning that one of the groups has an estimate larger than the other, then it has to be consistently positive for maximum number of times you do the same experiment in the same way from the same population. Okay, so that basically means that 95% of the times your estimate should be positive. If your estimate of mean difference is positive, then maximum 95% of the times it has to be positive, meaning that both of the confidence limits have to be on one side of 0. If they are on, if one of the confidence limits is positive and other confidence limits is negative, that basically means that there is a more than 5% chance that you are not going to get a consistent mean difference which is positive. Okay, so this concept of point of no return is one of the more useful utilities of confidence limits, because if you have knowledge of this, you don't even need to calculate a p-value. In fact, most of the times p-value is not really that useful compared to actually confidence limits. Okay. Now, this point of no return for the mean difference was 0. Okay. For other estimates, it can be different. Like for correlation coefficient, also it is 0. Like correlation coefficient, ranges from -1 to +1, meaning that -1 is perfect negative correlation, +1 is perfect positive correlation, and your no correlation is 0. Okay, so if your suppose your correlation coefficient came out to be positive, like suppose 0.4 or something, okay, and your confidence limits, 95% confidence limits for your correlation coefficient came out to be, suppose, minus 0.1 to plus 0.8. Okay, that basically tells you that your there's a more than 5% chance, or more than 5% of the times, if you repeat the same experiment, you are going to get a correlation coefficient which can be negative. Okay, that is a level of uncertainty that you're not okay with. So you are basically committing an alpha error, right? If your both of the confidence limits for a positive correlation remained positive, that basically tells you that more than 5%, there's a less than 5% chance that if you repeated the experiment your infinite number of times, your correlation coefficient will come negative. Okay, and that is a level of alpha error that you are okay with. Okay. So that this is for correlation coefficient. Similarly, for odds ratio, that straddling point is 1, meaning that if your odds ratio is more than 1, then confidence limits of odds ratio should also, both of them should be more than 1. Or if it is less than 1, both of them should be less than 1. Then you are going to get a statistical significance of less than 0.05, as well as you will be more certain of whatever your answer is. Okay. Similarly, for area under the curve of receiver operating characteristic curves, ROC curves, the area under the curve of 0.5 is like the middle ground. If both of them are above 0.5, both of the confidence limits are above 0.5, then you are okay. If one of them is less than 0.5, other is more than 0.5, then you're not going to be certain, or basically your statistical significance will not be reached. Okay, so this is the connecting point between your confidence limits and p-value. And this is the confidence limits are more practically useful than actually the p-value. This is how you see it. And with that, I'm concluding my presentation. I hope you people learned well from this. I would suggest that I've tried to repeat the topics multiple times. You understand, like, because one time saying doesn't really hit as well as you repeat the same thing again and again in different ways so that it sticks. I've tried to do that throughout this using some visuals and everything. And if you have not understood, I will suggest you go back and re-watch this, because this is the essence of standard errors and confidence limits. Okay. Now I tried to tie it down in multiple ways, and I hope this was useful. I'll see you in the next video. Thank you for watching.